Mm. Okay, so let's recall that in the previous video we have shown that symmetric groups of this type have p-Sylow subgroups, where p of course is a prime. And in the proof of that fact, we came across a kind of construction in which if we are given a p-Sylow subgroup of this, then we somehow were able to generate using that subgroup a p-Sylow subgroup of this. So let's see that in an example now. Suppose we consider S2. So now our prime is 2. We know what the elements of S2 are. There is that identity permutation and we have this transposition. The symbols on which these permutations are acting are of course 1 and 2 in this case. So what is the next group for this prime? It is S4. So say we seek a p-Sylow subgroup of S4. Then according to our construction in the proof, we first have to look at the set of symbols now we have. Now we have 4 symbols and then we have to divide this set into clumps according to our scheme. And the clumps in this case will be only 2, these. And then we generate that permutation sigma. In sigma we have of course a product of cycles. We first use the first elements of each clump. That gives us this transposition 1, 3, and then we use the second elements of the clumps. So that's how we get sigma. And then we would need a p-Sylow subgroup of S2. Now because S2 has order 2, its only p-Sylow subgroup is itself, which if you want you can also treat as the cyclic group generated by this transposition. It is just S2, that's it. So you call this P1 and then according to our scheme we have P2, which is sigma inverse P1 sigma. If one calculates this, one will get this. You just have to calculate the conjugates of these elements by sigma. That is sigma inverse E sigma is going to give you E again, and sigma inverse 1, 2 sigma you will see if you calculate will just be 3, 4. So this is our P2, which again is actually the cyclic subgroup generated by this transposition. And then you have that T, which is P1, P2, and this P1, P2 turns out to have these 4 elements. I urge you to actually do the calculations and see for yourself that yes, these things are like this. And then this of course is not the p-Sylow subgroup we are seeking in S4, but another step is there, and that other step is just considering this product, the product of T. This itself is a subgroup and the cyclic subgroup generated by sigma. This turns out to be the required p-Sylow subgroup in S4. So this way one can calculate. Okay. So that's just that. So now we are going to see a new definition, which actually is in a sense not new. We have already seen it before, but now we are going to see it formally. It's a relation on a group. So the definition is this. Let G be a group and A and B are, okay, because we have started the sentence with let me just write B here. B subgroups of G. We define a relation, more specifically a binary relation relating two elements in G. A relation denoted by this symbol in G as follows. For any two elements X and Y in G, we define X to be related to Y if Y is equal to AXB for some element A in the subgroup A and some element B in the subgroup B. We have already seen this in one of the exercises a few sections back. Okay. If you go through the sets of exercises, you will find this. This was I think the last exercise or the one before the last exercise in some section. And there itself we have shown that this is actually an equivalence relation on the group. And the equivalence classes have some structure. So the next lemma is about that. In fact, okay, I'm going to tell you what that exercise is. So let's state the lemma. Let G be a group and A and B be subgroups of G. The above relation, because we are not calling this, I mean, we haven't given this relation any name, so we are just simply saying the above relation. In fact, the equivalence classes that this relation generates are important and they have names more than the relation itself. The above relation is an equivalence relation on G. The equivalence class of any element X in G is the following set: AXB. This is just a symbol to denote the equivalence class, and you will now know why we are choosing this symbol. it is the set of all elements of this form ax, b. X of course is fixed, x is this element, but a and b vary like this. Okay, and we have already proved all these things in exercise 39 of section, the 5th section. Still, the author again asks us to prove these facts in case someone hasn't solved that exercise, but we did, of course. So we are just simply going to write the exercise number. C this. So we have this fact that this lemma is true, that we have such an equivalence relation on any group G for two given subgroups A and B, and the equivalence class of this any element X, it looks like this. Now these equivalence classes have names. The equivalence class is called a double coset, because two subgroups are involved. Like in a coset, a single subgroup is involved. Here two subgroups are involved, so they are called double cosets. A double coset of A and B in G, and these double cosets will be will help us in getting. You see, do not forget that the third proof of Syllow's theorem is not over. We have only so far shown in the previous video that these symmetric groups, not for any Sn but for this type of Sp to the power k, only this type of symmetric groups have p-Sylow subgroups. That much only we have shown, but we still have to show that any finite group G has a p-Sylow subgroup. Okay, so that job is still there, but in getting that we are going to use this fact, and this will later help us in getting the other parts of Syllow's theorem also, which the first two proofs did not give us. Okay, now there are some things that one can say about these double cosets, provided A and B are finite subgroups of G. So we are now coming to that, and that is this. Let A and B be finite subgroups of G. G may itself be infinite, but A and B are finite. We define we are going to define a map. What can we call it? We can call it F, or actually we can call it anything. I haven't written it here what the author is calling it, okay, in the text, so I'm just going to call it F, but very likely it's not F, but it does not matter because it is not something standard. We are going to define such a function by this rule is this function well defined? That is the first thing we have to make sure. Let's see. Actually, this function itself does not depend on finiteness of A and B. Even if none of these two subgroups is finite, still the function will make sense. But we need finiteness to say something about the function. Okay, so what is the function doing? Let us first see that. What is the rule of the function doing? Any element of the domain is going to look like this, of course, AXB, because that is the definition of capital AX, capital B. Now what f does to AXB is that it just multiplies AXB from the right side by the inverse of x. Okay, and that of course is going to be an element in AX BX inverse. Now you may get confused a little bit here. What exactly is this AX BX inverse? Just like AXB, it is simply this. In this set, the elements look like this, where again A varies freely over A and B varies freely over B. That's just it. But if one looks carefully, this is also something else. Do you remember that for any group, any subgroup B, you can consider XBX inverse? We did this before, and we also proved that this itself is also a subgroup of the original group G. So here what we are looking at is in fact a product of two subgroups of G. That's not the case here. Here, for example, if you think of this, you can, okay, due to associative law, you can think of this product as the product of the subgroup A and the left coset of B, XB. But that left coset is not necessarily itself a subgroup, okay, unless X is in B. Here, however, that's not the case. Here, this is a subgroup of G, of course, but this is also a subgroup of G. But we are coming to this fact a little later. Let us first see what this thing is. Is it well defined? So for well definedness, we have understood, since we have seen what this means, we have understood that the output lies in this set. Okay, so that is one part of being well defined. And the second part is that for a given input, there should be a unique output. So if you take, say, two inputs which are actually equal, but in taking two inputs, you have to be careful. If you write something like this, say these are two equal inputs, carelessly say you write this, then it's wrong, of course, because X is a given element in G. So X stays fixed here, but A and B are, they may change. Okay, so say you have this for some choices, A1 and A2 of elements from capital A, and for some B1 and B2 from capital B, you have this. Then does that imply that the corresponding outputs are also equal? Yes, of course. You just multiply these equal elements from the right side by X inverse. That's it. So the outputs are also equal, and this proves that for a given input there is only one output. So yes, the function f is well defined, it's a legitimate function. But if you run this argument in the other direction, say you are given two elements a1x b1 and a2x b2 in your domain, for which the outputs are equal. Say you start your argument from this equality. Can you go back? Yes, you can. But due to what? Because of what? Because of the right cancellation law. So this implication is in fact simply not an implication but an equivalence. And that proves that this function, besides being well defined, besides being a legitimate function, is also one-to-one. Okay, this is one-to-one. Now that you have f one-to-one, is it onto also? Ontoness is almost obvious. How? You choose any element in the second set. Some people call it range, some people call it codomain, it does not matter. To get rid of that confusion, I just simply call it the second set. So you choose any element ax, bx inverse. That of course is the f image of axb, where this axb belongs to the domain. So that is why the function is one-to-one and onto. It's a bijection. Alright. Now note this fact. Since A is okay, now only we are going to use finiteness of A and B, because A and B are both finite. Of course AXB is going to be finite, and this is itself is also finite. However, we do not need a bijection to see why they are finite, but the bijective map F now tells us that they have the same number of elements. That is the conclusion from this discussion. So this gives us the fact that the number of elements of AXB is equal to the number of elements of this other set. But okay, now on this, if you apply that thing what I was talking about right a while ago, that this can also be interpreted as the product of the subgroup A and the subgroup XBX inverse, then this type of products have their order in terms of a it's given by a formula. You recall what was the number? I think it is Theorem 251. If you go back to that section, you see Theorem 251. By that theorem, this is just equal to the order of A times the order of this subgroup XBX inverse divided by the order of their intersection. Okay. However, in the we consider this kind of thing, this kind of conjugate of a subgroup B by an element in one previous exercise, and there we proved that there is a bijection between B and XBX inverse, and which tells us that when B is finite, the number of elements in B is the same as the number of elements in XBX inverse. So we can write one more line and have this. That means if A and B are finite subgroups of a group G, and although we haven't written it explicitly, but it's there in the background, X is an element in G, then the double coset of X, the double coset containing X, AXB, has its number of elements given by this formula. We are now going to state this fact formally as the next lemma. Sometimes while going through a mathematics book, we may get bored seeing lemmas and their proofs one after another without any end. So there this kind of discussion is helpful. You see, you do not even know that you are proving something, but then when you get the result, you just state it. Okay, so that way the boredom is mitigated to some extent. Okay, so we are now going to formally state it. Let G be a group and A and B are finite subgroups of G. But this time let us write it, let X be an element in G. Then the number of elements in the double coset AXB of X in G is given by this formula. Okay, so that is the lemma. And now we are going to see the second step. Do you remember that in this third proof of Syllow's theorem, the author mentions of some steps. The first step was to show that those symmetric group Sp to the power k have p-Sylow subgroups. That we have done. So now comes the second step. But it's better to feed this a little ink also. In this second step, we are going to do that thing that we talked about previously. That is, if our group G is contained in a larger group, say M, which is also finite, G is also finite, contained as a subgroup of course, not just as a subset, and M has a p-Sylow subgroup, then G also should have a p-Sylow subgroup. So that is the next, this is also a lemma. This will be 2, 12, 5 after that one. Let M be a finite group having a subgroup G. Let M have a p-Sylow subgroup Q, where P of course is a prime. We need not write it again and again because we are in the middle of a discussion. So in the current context, P is a prime. Then G also has a p-Sylow subgroup. And in fact, we can say something about at least one p-Sylow subgroup of G. In fact, this is a p-Sylow subgroup of G. Do you see this one and this one? This is why we need this. In the proof, we are going to need this. So it's kind of going in the other direction, the direction opposite to what we took while proving that result, that sp to the power k has a p-Sylow subgroup. There we went from a smaller group to a larger group. Here we are given that a larger group has a p-Sylow subgroup, then a smaller one also has one. P-Sylow subgroup of G for some x in M. Now, how are we going to prove this? The proof actually is not that difficult, given that we have all the ingredients that we need. So the proof simply goes like this. What we are going to do is we are going to see a double coset decomposition of M, the larger group, but using which subgroups? Using G and Q. Note that our large group M now has two subgroups. Q is a p-Sylow subgroup of M, and there is G of course also sitting inside M as a subgroup. But before we get to this decomposition by double cosets of G and Q, let us see what these things mean. That's how the author started the proof. That is by restating what these things actually mean. So we are saying that Q is a p-Sylow subgroup of M. M is a finite group. That means Q has some order which is a power of this prime P. Let that power be p to the power M. That means p to the power M is the largest power of P dividing the order of M. No higher power divides the order of M. So this is one thing, and to also say that it's the largest, the next higher power does not divide the order of M. So now we know that the order of Q is p to the power M. Thus, also let the order of G be of this form, where n and t are integers and n of course is at most m, because the order of G by Lagrange's theorem also divides the order of m, so n cannot exceed m. Okay, and say this is the largest power of p dividing the order of G. So that means where t has no more p does not divide t. So we are now seeking a subgroup of G whose order is e to the power n, and the claim is that such a subgroup is of this form for some x in n. That is the claim. Now we are going to consider that double coset decomposition. Of m by G and Q. By G and Q or Q and G does not matter really in what we are going to do. So it is just this. M is written as a union of distinct double cosets of G and Q, where this x varies over a set of representatives. You already know these things, what we normally do when we have an equivalence relation on M. We write on a set, we write that set as a union of distinct equivalence classes. So that's what we are doing here. Okay. Since M is finite, this disjoint union will turn into an equation if we are talking about number of elements. This order of M will be equal to this, where the sum again runs over a set of representatives x. Okay, one x from each equivalence class. Now let us concentrate on this. By the previous result means that lemma by lemma 2, 12, 4. The order of Gxq is equal to the order of G times the order of Q divided by the order of G intersection xq x inverse. And because we know what these orders are in the numerator, we can write one more line. So order of G is p to the power n times t, and this one is p to the power m divided by this. Okay. Now since the subgroup in the denominator is a subgroup of Q. Oh well, it's not a subgroup of Q actually, but it's a subgroup of XQ inverse, and XQ inverse has the same number of elements as Q, which is p to the power m. Oh, okay. Yeah, wait, hold on. Is this going to give me something? Or should I consider, oh, I think I should consider it as a subgroup of G instead. Let's see if I'm following the right track. Since this is a subgroup of G, and I mean it is also a subgroup of this, but that's not going to give us what we want. It's at the same time as subgroup of G, and the order of G is this. So no, this again, okay, this again is confusing. I think I was right the first time. And equal to p to the power m. The order of this, it should divide that order by Lagrange's theorem. So it will also have to be some power of p for some integer. Integer means non-negative integer, of course, you understand that. Or let us just simply include that also in this condition. This. Okay. And now we also mention that since this is at the same time a subgroup of G, whose order we already know, we have mx less than or equal to n. I mean, see, again, now using the fact that this intersection is a subgroup of this, we have come to know the form of the order, the form of that number. It has to be a power of p, where the exponent mx does not exceed m. But at the same time, we now know that this number has to divide this. Since t has nothing to do with p when we are talking about division, so p to the power mx has to divide p to the power n. So mx also should not exceed n. And now the claim is this. We claim, note one thing, that whatever we have been saying so far, there we did not choose any specific x was anything. In fact, x was any x in these terms of the sum. But now we are claiming that mx is equal to n for some element x. This is our claim now. Suppose this is not the case, i.e. each mx, no matter whatever x we are going to choose, each mx is strictly less than n. Then what do we get? Then let's look at this order. Already the numerator had some form p to the power n plus m times t, but now the denominator also we know what type of number it is, p to the power mx. And if you write it even more compactly, then you get n minus mx plus m in the exponent times t. Now you look at this exponent, because no matter what x is, mx is less than n. So this n minus mx is a positive integer. So its least value can be 1, or it can be even more. That means in any case we are getting at least m plus 1 in the exponent. Or in other words, this number is divisible by p to the power m plus 1. Then this is that too for every x in M. But then what is the consequence of that? But then order of M equal to that sum gxq, not p, is also, you see, all the terms in this sum are divisible by p to the power m plus 1. So order of m should also be divisible by that number, that power of p, is also divisible by this. This, however, is a contradiction, because according to what we according to how we started the proof, p to the power m was the largest power of p dividing the order of m. This one does not, it should not divide the order of m, capital M. But this is a contradiction. So that means our supposition is wrong. So whatever we are claiming here is actually true. There is at least one element x in M for which that exponent mx must be equal to n. Hence, the claim So let x be an element in N such that mx is equal to N. Then what? If mx is equal to N, then okay, then what can we say about the intersection? Let me just go back to the intersection. G intersection x cube x inverse. This is, oh okay, yeah. We need not go back to this again, but we just need to consider this intersection. Then the order of this intersection is p to the power n. Okay. So if the order of the intersection is p to the power n, then of course this intersection becomes a subgroup of G. It is already a subgroup of G, but now its order is that order which we were seeking from G, p to the power n. It's not p to the power n times t, it's not equal to G. That's not what we are saying. We are just simply saying that this is a subgroup of G whose order is the largest power of p that divides the order of G. Hence, p equal to, so I also misunderstood this last part of the proof. That's why I got confused, but now it's clear to me as well. Hence, this is a p-Sylow subgroup of G, and that completes the proof. Now we have all the ingredients to finally complete this third proof of Syllow's theorem in just a few lines, like this. Suppose G is a finite group. Okay, say its order is n. Then by Cayley's theorem, G can be isomorphically embedded in Sn. If you go back to Cayley's theorem, you will see that in the proof of Cayley's theorem, if we are given any G, not necessarily finite, but in this case we have a finite G, the set of elements on which we are going to consider that group of permutations that we have in the proof of Cayley's theorem, that set is taken as G itself. In particular, if G is finite, then the corresponding permutation group becomes this symmetric group Sn, where n is the order of G. And we find an isomorphic copy of G inside Sn. That's what Cayley's theorem gives, or rather its proof gives us. But now our prime P is already there. Okay, it is already given, but we can choose an exponent large enough so that p to the power k exceeds n. Then we can isomorphically embed Sn inside Sp to the power k. Exactly how I am not going to say, it's extremely easy. What you do is, okay, let me just give you a hint. The set of symbols on which the elements of Sn act is this set, all the positive integers up to n. But then it continues and we get this. This is the set of symbols on which the permutations in that is the elements in this group act. So you just consider in sp to the power k those permutations that fix these symbols that appear after n, that is n plus 1, n plus 2, all of them. That set turns out to be the copy of Sn in sp to the power k. That's it. It's very easy to show. But then, using these two embeddings, you get a copy of G inside sp to the power k. Okay. Now, using that first lemma or theorem, whatever it was, this has a p-Sylow subgroup. So that is why using this one right now we have done it. G also has a p-Sylow subgroup, and we have also seen a kind of a form of the p-Sylow subgroup, at least one p-Sylow subgroup, and this will later be used in knowing the other p-Sylow subgroups also in the second part of Syllow's theorem, which we are not going to see today. So the second and third part of Syllow's theorem we will see in the next group theory video. So that's just it for tonight. Our next upload is this when? I forgot. Today is Tuesday, right? So Wednesday, Thursday. On Thursday we are going to see the next upload. So that's just it. See you on Thursday then. Until then, this is me, Lucifer from a mathematical room. Have a nice night.